Lesson 921, the t-distribution and t-statistics. Previously, we have seen that under certain conditions, the sampling distribution of sample means is normally distributed. As with any normal distribution, we are able to standardize a distribution of sample means by finding z-scores. If we can do this if we know the standard deviation of the population. But what happens when we don't know this? Often we do not know population standard deviations. In this lesson, we will confront the reality that population standard deviations are rarely known. Not knowing the population standard deviation influences the way we perform statistical inference regarding the population mean. So first, when sigma is known, and remember that sigma, that stands for the population standard deviation. So suppose we have a population whose standard deviation sigma is known. If the population is normal, or the sample size is sufficiently large, meaning n is greater than 30, a sampling distribution of sample means is approximately normal. That's what we just learned in the previous lesson. The standard error of the sample means is given by sigma sub x bar equal to sigma divided by the square root of n. That's one of the formulas that we saw in the previous lesson. The standardized value, the z-score, of a particular sample mean x bar from a sample of size n is called a test statistic, or z-statistic, and is computed with the formula that we saw before, z equal to x bar minus mu divided by the fraction sigma over the square root of n. Since the sampling distribution is normal, the distribution of the test statistic, the z-statistic, is also normal. In this case, the standard normal distribution describes the variability in the test statistic. Recall that in Module 7, we used z-statistics to perform hypothesis tests about population proportions. So now, when sigma is unknown. In most situations, we do not know the population standard deviation. Another way of saying this is that sigma is unknown. The only option available to us is to approximate sigma with a sample standard deviation, s. To do this, we need to substitute s for sigma. So again, notice that lowercase s is the symbol that stands for sample standard deviation. That's something that we saw back in Module 2. When we make this substitution, the standard error of the sampling distribution is estimated by the fraction s over the square root of n. We're just estimating sigma with s, so that fraction has changed. The test statistic for a sample mean is then x bar minus mu divided by the fraction s over the square root of n. Since the sample standard deviation s varies from sample to sample and only approximates sigma, its use in the test statistic calculation introduces additional variability in the test statistic. The added variability means that the distribution of the test statistic is not normal. The test statistic actually varies according to what we call the student's t-distribution. Off to the right there, the language tip. Note that instead of saying the standard error of the sampling distribution is given by, we say it is estimated by. Again, that is because we changed out s as an approximation for sigma. So now we're going to describe this t-distribution. The t-distribution describes the variability of the test statistic. So capital T is equal to x bar minus mu divided by the fraction s over the square root of n when the sampling distribution of sample means is normal and a sample standard deviation s is used to estimate the population standard deviation sigma. This test statistic is called the t-statistic. Like the z-statistic, the t-statistic is an estimate. It estimates how many standard errors the sample mean is from the hypothesized population mean. The t-distribution is a family of continuous probability distributions. The width of a t-distribution depends on how much a sample standard deviation can vary. The amount of variability in a sample standard deviation depends on how many deviations vary freely when it is computed. To the right there, to vary freely means to vary without bounds or limits. The sample standard deviation is computed using the formula below. We saw this in Module 2. The deviations from the mean, x minus x bar, are averaged in sample standard deviation. When the deviations are added together, they always add to 0. Because of this, the last deviation summed in this average is not free. It is always the value that makes the resulting sum 0. There are n deviations from the mean, but only n minus 1 of these are free deviations. So this actually answers a question that we might have had from Module 2. Why, when we were averaging, did we divide by n minus 1? It was because we only had n minus 1 free deviations. The last one was not free. It had to be the one that made the resulting sum equal to 0. The variability of standard deviations depends on the number of free deviations in the sample standard deviation n minus 1. This quantity is known as the degrees of freedom. So degrees of freedom we're going to relate with n minus 1, the number of free deviations. Technically speaking, each degree of freedom defines a uniquely associated t-distribution. It is important to know that the fewer the degrees of freedom, the more the sample standard deviation varies. In other words, the smaller the sample size, the more the sample standard deviation varies. So the smaller the sample size, the greater the variability in a t-distribution. That's actually related to what we've seen before. When we have a small sample size, we have more variability. But when sample size increases, we decrease the variability. T-distributions have the following characteristics. T-distributions are bell-shaped and symmetric with a mean of 0. Each t-distribution depends on the degrees of freedom, which we're going to abbreviate df. T-distributions have heavier tails and narrower peaks than the standard normal distribution. The area under each t-distribution curve is 1. As the degrees of freedom increase, the tails are thinner. As the degrees of freedom increase, the t-distribution eventually approaches the standard normal distribution. And when making inferences about a population mean, the degrees of freedom are equal to the sample size minus 1, which means df is equal to n minus 1. Again, that's going to be something that we'll be using. So a lot of what was just described there you can see in this picture here. Notice that 0 is in the center. You can see that the t-curves that they've described for degrees of freedom 5, 2, and 1, they appear approximately bell-shaped, symmetric. You can see the descriptions about the tails and the peaks. And you can see that as the degrees of freedom is increasing, these curves are getting closer to the normal curve that is at the top. So next, let's try these. Researchers are very worried about how quickly sea ice is melting. If sea ice continues to melt, it is possible that polar bears will become an endangered species. That means that eventually there may be no more polar bears anywhere in the world. Polar bears use the sea ice for hunting and making their dens. Also, as the ice melts and erodes, there are smaller seal populations. Seals are the polar bear's main source of food. This further endangers the polar bear population. Biologists regularly visit Arctic regions to track the health and numbers of polar bears. One important measurement is the weight of adult male polar bears. Biologists estimate that the average weight of an adult male polar bear is approximately 475 kilograms, which is the same thing as 1,050 pounds. For the questions below, assume that polar bear weights are normally distributed. So first, number 1. Suppose that 4 random samples of 5 polar bears are drawn from 4 different areas in Alaska. The weights of the polar bears in kilograms are displayed in the table below. So here we have the first sample, sample A, and there's the 5 polar bears to the right. Second sample, which is the second row, sample B, there's the 5 polar bear weights to the right of that, and then sample C and sample D. Part A. All of the samples have the same sample size. What is the appropriate number of degrees of freedom for this sample size? So first of all, the sample size is how many bears in each sample. So sample size would be 5. And we could also say that that's n equal to 5. So then degrees of freedom, df, would be n minus 1, which is 5 minus 1, which is 4. So that's how many degrees of freedom would be appropriate for that sample size. Next, part B. What are the means and standard deviations for each sample? Complete the table below. For this, we're going to want to use our graphing calculator. We can easily find the mean with a simple calculator, just adding each weight up and then dividing by 5. But the standard deviation, that would take a lot of time if we're using the formula. So for this, we do want to use our TI-83 or 84. And the way that we would do that is with lists. So we have to go to Stats. And then on the first screen that comes up, we want to choose Edit to edit our list. And then we want to enter in the polar bear weights in each list. So for the first list, L1, I'm going to put the weights from sample A. So 466, and then 520, 512, 513, and then 498. And while you're on this same screen, you might as well enter in all the other polar bear weights into the other lists. So sample B will be in list 2, 471, then 476, 461, 453, and 423. And then list 3, that would be sample C. So the first polar bear weight in sample C is 493, and then 482, 431, 450, and 452. And then list 4, that will be the polar bears from sample D. So the first polar bear in sample D is 481, and then 492, 475, 498, and 512. And then it's always a good idea just to go back over your lists just to make sure that you entered all of those numbers in correctly. And that looks good. So what we can do with these lists, once we have everything entered, on the TI-83 or 84, again push the Stats button from this screen. And then what we're going to go to is using the direction button with the right arrow, go right, and we can see one variable statistics. So we're going to do this for each of those 4 lists. So I'm going to choose one variable statistics by pressing enter. And then I want to use list 1. It's already entered there. I don't need anything in the frequency list, so I'll go down to calculate and push enter. And so here you can see it says X bar is equal to 501.8. And then the standard deviation that we want to look for is where it says capital SX. So S for the sample standard deviation. And you can see it says 21.545. So you can do this with each of the 4 lists. So go ahead and do that on your own. I'm going to go back to the worksheet and I'll put in these numbers and then I'll write down what you should get from the other mean and standard deviations so you can check that against your calculator work. So we had for sample A, the mean was 501.8 and the sample standard deviation was 21.545. Do one variable statistics for the other lists, and what you should get for sample B is a mean of 456.8 and a sample standard deviation of 20.885. For sample C, the mean you should get is 461.6, and then the standard deviation should be 25.324. And then sample D, the mean you should get is 491.6, And the sample standard deviation you should get is 14.536. So now that we have this sample data, we'll move on to part C. Calculate the t-statistic for each sample. Assume that the population mean weight, mu, is equal to 475 kilograms. Complete the table below. So the formula that we are going to use was given before, capital T equal x bar minus mu divided by the fraction s over the square root of n. N is our sample size, so that's going to be 5 for all of these calculations. Mu was given as 475, so that's going to be the same for all of these. But for each sample, we have a different x bar and a different lowercase s. So for sample A, you would have t is equal to the mean that we had from sample A was 501.8. And then the mean is 475. And then the standard deviation for sample A was 21.545. And then that is divided by the square root of n. I recommend trying to do this in a couple of steps, but you can use your graphing calculator to calculate this all at once. You just need to use some parentheses to do that. So for the numerator, parentheses 501.8 minus 475, and then divided by, in the denominator, I need another set of parentheses, so parentheses 21.545 divided by the square root of 5. And then press enter, and you should get 2.781. So on your own, use the formula and calculate the rest of the t-statistics. And you can check your work against these results. So for sample B, you're going to get negative 1.949. Just like z-scores, we can get negative t-scores. For sample C, negative 1.183. For sample D, 2.554. All right, finally we have some follow-up questions for this whole example. So part D, which of the 4 t-statistics in the previous question shows a sample mean that is farthest away from mu equal to 4.75 in estimated standard errors? So this is just like how we interpreted z-scores. We want to think that a score that is farthest from 0, which is at the center, that would be the one that is the answer for part D. So in this case, we have 2.781, negative 1.949, negative 1.183, and 2.554. The one that is farthest from 0 would be sample A. The secret word for this lesson is bear. Part E. Which of the 4 t-statistics indicates that the sample means are below mu equal 4.75? If we think of the word below, this would match up with the negative t-scores. So that would be samples B and C. Part F, which of the 4 t-statistics indicates a sample mean that is closest in estimated standard errors to mu equal 4.75? Again, doesn't matter if it's positive or negative, just what's closest to the center, which would be where 0 is for the t-scores. This is sample C with negative 1.183. And then finally part G. Based on the sample statistics, which sample or samples should biologists and conservationists be most worried about? Note, conservationists are people who are interested in conserving or saving endangered animals or plant life. So if we think about trying to save endangered animals, and that what we were finding before were the mean weights and standard deviations for these samples of polar bears, what these conservationists would be concerned with is if the polar bears are underweight, as that would show that they are not getting enough to eat. So then we'd be focused on the t-statistics that are negative, and what's most concerning is the one that is the most negative, so sample B.